All right, we're going to take a look at some example problems for using what are called ice tables. I sometimes call them a rice table to remember that the reaction of the chemicals is at the top. So this is a way for finding the equilibrium constant, KEQ, in this particular example from the initial concentrations and one of our equilibrium concentrations. So we'll just take a look at the example problem that's done, and then we'll try a few more so that you guys can work through them. So a student placed 7 moles of NH3 in a 0.5 liter flask. At equilibrium, 6.2 molar nitrogen was found in the flask. What is the equilibrium constant, KEQ, for this reaction? So we've got our chemical reaction here. You can see that it's written here. So we're going to set up what's called a ice or rice table. So that represents the initial, so the reaction is at the top, the initial concentrations of our chemicals, the change in concentration, and then the concentration at equilibrium. This is where we can calculate KEQ from, the equilibrium constant. So we need to get all of those values to be able to calculate it. So you notice that they go ahead on this side here, they calculate the moles per liter to find the molarity of the NH3. So 7 moles divided by 0.5 is 14. So your initial concentration of NH3 is 14. It doesn't mention any initial concentrations of the other two chemicals. It just says that the NH3 is placed in a flask. So we go ahead and assume that they are 0. The other thing it does tell us is that at equilibrium, so on our equilibrium line, N2 is 6.2 molar. So we can fill in the numbers we know. All the numbers we're placing in here are going to be molarities. So we don't have to worry about writing all our units right now. We're just trying to fill out our little table. So what we can do is we are going to look first at the column that has the most information, and that's our nitrogen in this case. So our change is going to be adding or subtracting a number to make this basically a true math problem. So we're trying to make this add up. So 0, we would have to add 6.2 to that to get 6.2 at equilibrium. All right, so we're just making sure that that works. So that's where they got this 6.2 from. Now, the other thing about the change line is that it is dependent on the mole ratio. Okay, so this is where we're going to relate the amounts to each other. So I'm going to go to the left first. So since, or actually I'll do hydrogen because they're on the same side of the reaction. So if I'm adding 6.2 molar nitrogen, then I'm going to also add to the hydrogen because they're both on the same side. I'm increasing my amount of products. Now hydrogen, it's a 1-to-3 ratio to hydrogen, so hydrogen is going to make 3 times that amount. So you can see down here they put in 18.6. Okay, so that's where that comes from. So it's 3 times 6.2 is how they got 18.6. Okay, and that's just based off hydrogen being 3 times bigger. Now you'll notice on the other side that it is subtracted because we are using the NH3 to make these. So one side of the reaction is always going to be adding, the other side is going to be subtracting. They're always going to be opposites of each other. So if we're making more nitrogen, we're adding to it, then we have to subtract from the other side. And this is a 1-to-2 ratio. So we're going to subtract twice as much. And that's where they get this 12.4. Okay, so that's where all of these numbers come from. So this is 2 times, the 6.2. All right, and we're subtracting it. So then we do the math, okay? Just like we did the math in the first, or in that middle column, we're going to do it here. So 14 minus 12.4 gives us 1.6. We've already got our 6.2, and 0 plus 18.6 gives us 18.6. So these are all of our equilibrium concentrations. So now that we have those, we can set up our equilibrium expression. So as we've seen, that's our concentrations of our products raised to their coefficient power. So hydrogen's to the 3rd power because we have a coefficient of 3. Oops, you guys can't see that. There we go. Hydrogen's to the 3rd power because we have that coefficient of 3 in our reaction. And we're dividing by our reactant, NH3, squared because it has a coefficient of 2 in our reaction. So we're going to take these numbers from the equilibrium line and plug them in. Make sure you're cubing and squaring appropriately. and then calculate your answer. I would go ahead and just try this in your calculator. Make sure you can get 1.6 times 10 to the 4th, just so you know that you're on track. The other thing is your significant figures. So we look at all three numbers. We have 2, 2, and 3. So we're going to round to 2 sig figs. All right. So we're going to take a look at the next one, the practice problem. So you guys have another example and we can walk through it fresh. So it says the following gases were placed in a 4-liter flask, 8 moles of nitrogen and 10 moles of hydrogen. After equilibrium was achieved, 1.2 molar NH3 was found in the flask. So this one's already in a molarity, so I'm going to go ahead and put that in. So it says after equilibrium, so at equilibrium we have 1.20 molar NH3. Again, all your units should be molarity, so we're going to just leave out the units for now. Simplify our table. Now, we do have 2 other values, but they aren't in molarity yet. We have 8.00 moles over 4 liters. So 8 divided by 4 gives us 2 molar for the nitrogen. So that's, it says they were placed in there, so that's going to be our initial. And then same thing for hydrogen. We've got 10.00 moles over 4.00 liters. So 10 over 4 is 2.50 molar. So that's our initial of hydrogen. And it doesn't say any NH3 is placed in the flask. So we've got all of our given information in here. We need to find our equilibrium values so that we can find our equilibrium constant. So I'm going to look at the first column that is mostly filled in, which is NH3. To make this math problem true, right, I need to add 1.20 to make that true. And now we're going to use our mole ratio. So if I'm adding 1.2 on this side, I'm going to subtract on the other side. It is a 2-to-1 ratio for nitrogen, so it's half as much. So half of 1.2 is 0.60. And then we need, we can relate these together because this is a 1-to-3 ratio. It's always easier to start with something that's a 1-to-something ratio. So hydrogen is going to be 3 times bigger than this. So 0.6 times 3 is 1.8 molar. All right. So 2 minus 0.6 is going to give us 1.40. And 2.5 divided by, minus 1.80 is going to give us 0.70 molar. So those are our concentrations at equilibrium, and we're going to use that to calculate our equilibrium constant. So we're going to set up our expression. So products is NH3 to the 2nd power because of its coefficient, divided by the reactants, nitrogen to the 1st power, hydrogen to the 3rd power. We can see that this is the opposite of the first reaction. Okay. And we're going to go ahead and plug in our numbers. 1.20 squared over 1.40 times 0.70 cubed. If we look at all those, we are going to have only 2 significant figures in our answer. So putting this in, I'm going to do my 1.20 squared. I'm going to divide by my 1.4, and then I'm going to divide by 0.7 to the 3rd power. So we get 2.998. So to round that to 2 significant figures, we would need 3.0 for our equilibrium constant. All right, so that's how we can use these ICE tables to help us out. So we're filling in all the information that we know and then calculating from there. There are 2 more on the next page for you to try out, and you can always check with me in class if you need some more help. The 3rd one, you'll notice, has this part scribbled out. Now the reason is because it is a solid, so solids are not included in our equilibrium expression, but we will need to use that to help us figure out the change line, so be aware of that. you can kind of jot it down or do it to the side so you can figure out that change line. So try those out, and I can check them and help you out in class if you need to. Thanks. All right, now that you have had the opportunity to practice some of the ice tables, we're going to take it a step further and look at how do we determine our equilibrium concentrations of our chemicals using our ice table when we do have the equilibrium constant, okay, and we have our initial concentrations. So if we know what equilibrium constant it's going to achieve, how do we figure out what those concentrations end up being? All right, a little bit different approach, but we're going to use some of the same strategies. So it says, this is the example on page 218 in your book, so you can follow along. The following gases are injected into a 1 liter flask. We've got 1.2 moles of hydrogen and 1.2 moles of fluorine. So we can see just right off the bat, those numbers are down here. It is, we would have to take our moles and divide it by liters, but we're dividing by 1. So our molarity, again, we always want to put molarity into these, is 1.2 for each of them. And now it doesn't give us a concentration for HF, so we can assume it's 0, just like we did before. It says, what will the concentration of HF be when equilibrium is achieved? So we want to know this box here. That is our ultimate goal in this question. It says, there is no dilution effect when gases are mixed because the mixture's volume isn't increased. So it's a little side note. Injecting another gas into the same flask is possible because there's so much space between gas particles. So when we mix these gases, we don't have to be worried about anything adding together for them in terms of their pressure, volume, or moles. Okay, so we have our ice table, which is provided, and we're looking for this value down here. You'll also notice our reaction up here, it gives us our equilibrium constant. So instead of trying to find that, we are provided with it. Okay, so if we think about this, we have our equilibrium constant. We can still write an equilibrium expression, our products squared over our reactants, H2 and F2. So we know that this value on the left side is 2.50. Okay, so we could replace that with 2.50. What we don't know is what these values are, and specifically HF. So we want to use that information to help us out. We do know where the concentrations are starting though. So it says set up its algebraic solution using coefficients in the balanced chemical equation to relate the moles of the reactants consumed to each other and the moles of product formed. Okay, so what does that mean? Well, we don't know how much is being added or subtracted from our chemicals, but we can use a variable. We can use X. So we know that we are starting with reactants, we have no products. So we have to add to our products and subtract from our reactants. So I like to put in my positives and negatives first, just so I have that clear. And again, we want to treat the two sides of the reaction separately. Then we're going to go ahead and say, okay, we don't know how much is being lost of this chemical, so we're going to say it's X. We don't know how much is being lost of this, but it's X. And that's a 1-to-1 ratio, so those values are going to be the same no matter what. The same amount is going to react for those two. For our product side, we're going to be adding an amount, X, but we are going to be comparing again to our other chemical, and we're going to make twice as many moles of HF as we have of each of those. So we're going to add 2X to this side. Okay, so again, this is where we incorporate the mole ratio, our coefficient. Oh, I always put an N on that. Our mole ratio with our coefficients. Okay, so this is 1X, 1X, and 2X based on their coefficients. So now our bottom line, as you can see, is just setting up that problem. So we don't know what X is, so we have 1.20 minus X, 1.20 minus X, and then 2X for our values. So what they do next is, just like we did up here, is set up the equilibrium expression, and then we plug in what we know. Well, at equilibrium, our concentration of HF is 2X, and hydrogen and fluorine are 1.20 minus X. Now they went ahead and put that as one term and squared it because they're the same, so we're multiplying the same term by itself, so it's squared. And that is equal to the equilibrium constant, which we had up here given in our question. So this is really our equation that we're trying to solve, okay? We've got that information. We need to solve for x. Now, the ones we're going to see in this class, you'll see our nice perfect square numbers, so we can deal with that by taking the square root of both sides. So if we take the square root of this side, then it gets rid of our squares, and we come up with this, simplifies it. And then the square root of 2.5 is 2.5 to the 1/2 power, same idea as the square root, and we get 1.58. Okay, so we have this part simplified to 1.58, so that equals 2x over 1.20 minus x. Now they start to simplify this. We take this bottom part here and multiply it to the other side, so we have 1.58 times that term, and that equals our 2x. Then we distribute the 1.58, and so we get this term here. Gather our x's, so add the 1.58 to the other side, so we get 3.58x equals 1.896. It's a weird font. And then divide by 3.58 on both sides. And that's how they get x, is 0.530 molar. Now, this doesn't answer our question. You'll notice on the left side over here, it says, don't forget to answer the question. The question is, what is the concentration of HF at equilibrium? So what we need to do is look back at that equilibrium and say, well, it's 2 times our x value. X is not our answer here. It's just helping us get there. We know that x is how much of these are reacting, but we're going to add twice as much because of our mole ratio there. So HF's concentration at equilibrium is 2 times x, so 2 times our 0.530, and we get 1.06 molar. Okay, so that is how we approach these problems. We're going to use an x to help kind of get us there and hold a position as a variable for us. All right, so we're going to work through another question like that together, which is on page 220 in your book. Page 219 does have another example, but this is a type of question we don't have to do in AP Chem, where it establishes an equilibrium and then shifts it. So we're okay with those. All right, so it says, in the lab, 4.5 moles of HCl are pumped into a 3-liter flask and heated to 80 degrees. How many moles of chlorine will be found in the flask after equilibrium is established? So we're looking for chlorine at equilibrium. So there's our question. And we have our equilibrium constant at 80 degrees is 0.36. You'll notice that it mentions the 80 degrees Celsius. If we changed our temperature, it can shift our equilibrium constant. So it's just saying that this is the equilibrium constant for the temperature that this reaction is happening at. So we don't have to worry about the 80, just kind of clarifying it. All right, so let's take the information we have and place it in our table. So we have 4.5 moles of HCl in a 3-liter flask. So we do want that molarity, 4.5 moles over 3 liters, 0.00. So 4.5 divided by 3 is going to give us 1.5 molar HCl. So we're going to start with 1.5 molar HCl. That's the only thing placed in our flask to start with, so we're going to put zeros for our other 2 chemicals. Now, we don't have any other information, but we do have our equilibrium constant. So when you're given that, that's a clue to know that we're going to have to use X to solve this. So if we look at this, our 2 sides of our reaction, we're starting with reactant. We have no product, so we're going to have to add to the product side, subtract from the reactant side, and then we're going to use X. On this side, we have a coefficient of 2, so we're going to subtract 2x. This side, our coefficients are 1, so we're going to add 1x. So we just make it match our coefficients. And then we bring everything down. So 1.5 minus 2x. We have x and x there. So whatever our concentration, or whatever our value is for x, is going to be our concentration of chlorine at equilibrium. That's what we're looking for. So now we can set up our equilibrium expression. Products hydrogen and chlorine each to the first power, over reactants, HCl squared. And we can plug into this what we have. So we know the equilibrium constant is 0.36. And then H2 and Cl2 are each x, so we have x times x. So I'm going to go ahead and summarize that as x squared. And then we have 1.5 minus 2x, and we're squaring that term. So we can see the top and the bottom are both squared. So we can take the square root of both sides of our equation. The right side is going to simplify to x over 1.5 minus 2x. It gets rid of our squares. And then we have the square root of 0.36, which is 0.60, right? Square root of 36 is 6. All right. Now we need to do a little rearranging. So we've got this term in the denominator, 1.5 minus 2x. We're going to multiply that to the other side. So we get 0.60 times 1.5 minus 2x. And that's equal to our numerator, x. We want to distribute this through, so I'm going to keep going over here. So 0.60 times 1.5, 0.6 times 1.5, is going to give us 0.90, keeping our sig figs, minus 0.6 times negative, or times 2 is going to be 1.2 x, and that's equal to x. So we're just using all our algebra skills now. And just switch colors here. We want to add this 1.2x to both sides to gather our x's together. So we get 0.90 equals, we've got 1x plus 1.2 gives us 2.2x. So be careful with that. Make sure you're adding that 1 there. Okay. And then we want to, oops, sorry about my clicky pen. We want to isolate our x, so we divide by 2.2 on both sides. And we get that x is 0.9 divided by 2.2. And we get quite a long number in our calculator, but we've got 2 sig figs, 4.1 is going to be our x value. Now again, we want to make sure we're answering the question. So the question asks how many moles of Cl2 will be found in the flask after equilibrium is established. So we are going to have 0.41 molar, because that's our x value is our molarity of chlorine, Cl2, but we want moles. Our molarity represents moles per liter, so if we can get our liters to cancel, our volume to cancel, then we are left with just moles. So we can multiply by our volume of our flask, which is 3 liters, and 0.41 times 3 gives us 1.23 moles of chlorine. All right, that's equal to. So that's kind of an extra step on this one. Sometimes it might ask for what's the concentration of chlorine, that kind of thing. This one asks for the moles specifically. Okay, so that is our final answer there, 1.23 moles of chlorine. So it's a little bit more complex in terms of our algebra here to do this kind of problem, but it is just using algebra. Okay, we're just flexing those muscles that we've had for many years. All right, so when you're always going to have something that's either already simplified, like an x over a term like this, or they're both going to be squared to make it an easy square root. Okay, we're never going to have anything in this class that requires a quadratic formula. That is possible with these kind of questions, but in AP Chem, they've taken that off the test. All right, so try number 2. Again, if you get stuck, let me know. Skip number 3 on this page, okay? It's not applicable to what we need to do in our class. And then the next part is determining initial concentrations from our equilibrium. So we're going to take a look at this one. If you want to pause and practice some of the questions before you look at this, that'd be a good idea. So for this one, it says determining past conditions from present ones is perhaps even more remarkable than predicting future conditions. So here, sometimes we're given the initial and we're kind of predicting what the future, the equilibrium will be. Going backwards is kind of more interesting, I think. So what we're going to be doing is still using X for some of our values. We're just going to see that the math kind of works out a little bit differently here. So it says some C3OH was injected into a flask where it established equilibrium with the concentration of carbon monoxide at 0.15. So that's at equilibrium. So you can see in the table they put the 0.15 here at equilibrium. What is the initial concentration of C3OH? So we do not know. We know that that was placed in the flask. We don't know how much. So they put X. And we know there's nothing else placed in the flask. So we can still put those as 0. So this one, we do have some information. We can kind of back calculate some of it. So we know that this column has the most information. So to make this true, we would have to add 0.15, right? So again, this line is our mole ratio line. So this one is on the same side, so it would also have to add, but twice as much because of the coefficient, so 0.30. The other side of our reaction would have to subtract because it's a reactant, and it's a 1-to-1 ratio, so it would have the same amount, 0.15. From there, we can go ahead and solve for equilibrium amounts. So X minus 0.15 is our equilibrium there. We're adding 0.3 here, and we've got our 0.15. It's already there for us. So we're going to set up the same way. You can see at the top, we're also given that equilibrium constant. So that's going to help us out. So we can set up, as you see at the bottom, an equilibrium expression. So our products over our reactant. And then we can plug in this line, that equilibrium line. So our hydrogen is 0.3 squared. CO is 0.15. And then we're dividing by X minus 0.15. That is equal to our equilibrium constant, which we have up at the top is 0.040. So we can now simplify this part and find our answer. So if you notice, they went ahead and multiplied this piece to the other side and then divided by this part and moved it down here. So those two pieces can switch. Your denominator and then the other side of your equation can switch places like that. Okay. It's very similar to if we had like density is mass over volume. Well, volume would equal mass over density. We can switch these two, right? Same idea. Okay, so that's kind of a little trick and a shortcut here. So that gets X all on one side, and then we can simplify the left side, get a value. So if we did that, we'd have 0.3 squared times 0.15 divided by 0.04, and then we would need to add 0.15 to that from the other side of the equation to get our X by itself. So that's how they get the 0.49, rounding to 2 sig figs. So X is 0.49 molar, and that gives us our X value. Now, that is, if we look, does that continue? No, they just put it all on this page. Okay, so we want to make sure that we answer the question. The question asks, what is the initial concentration of C3OH? So our concentration of CH3, oops, OH would equal, and our initial concentration is X, so 0.49 molar. I think that clearly shows your answer a little more than just leaving it as X. Okay, so this is kind of doing the same type of thing, using X as our missing piece, but in this case it's that initial concentration instead of one of the other ones. So again, we've got some examples, some practice problems. So why don't we do one together, and then on page 222, next page, and then you can practice some more ice tables in your book with your assignment. So this one says nickel sulfide reacted with oxygen in a 2-liter flask. When equilibrium was achieved, 0.36 moles of SO2 were formed in the flask. What was the original oxygen concentration in the flask? and KEQ is 0.30. So we've got our reaction written up at the top. Notice that they've scribbled out the solids, so we don't really care about those solids because they do not affect our equilibrium constant. So let's take a look at what we have. So we've got a 2-liter flask. So we're reacting this with oxygen in a 2-liter flask. When we reached equilibrium, 0.36 moles of SO2 were found in the flask. So 0.36 moles in our 2-liter flask, 2.0 liters. So 0.36 moles divided by 2 liters is 0.18 molar for the SO2, and that's at equilibrium. So we have that. We want to know that original oxygen concentration. We want to know what that value is there. Okay, so we start with just these chemicals. We're not starting with any SO2. But we also want to follow that coefficient. So we know that whatever's reacting, whatever this amount is, oh, sorry, never mind. More what I was going to say. All right, so we're going to go ahead and see what our change line is. To make this true, we would have to add 0.18 to get this equilibrium amount, right? This is kind of like a math problem here. We'd have to add 0.18. So to get from SO2 to O2, we need to do our mole ratio here. And this one's a 2-to-3 ratio. So to do that, the easiest way is we want to take our point, do this up here. So 0.18 moles, or molar SO2. And then it is a 2 moles of SO2 to 3 moles of O2. 2-to-3 ratio. So we want 0.18 times 3 divided by 2 to give us our proper ratio. So that gives us 0.27. So we are going to subtract 0.27 from our oxygen. Okay. So that's an easy way. You can kind of do a side mole ratio to help you out there. So we've got X minus 0.27. 0.27 as our equilibrium amount, and we've got our 0.18 for SO2. So we need to find our X value here. We got to find what that initial concentration of oxygen was. So we're going to use our equilibrium expression. Products over reactants. Again, we don't include solids. So we have SO2 squared divided by our concentration of O3 cubed, and we're not going to include the other solid. And we can go ahead and replace these with our values. So KEQ is 0.30, SO2 is 0.18 squared, and O3 is X minus 0.27 cubed. So we are going to simplify this a little bit. First thing I would do is, just like in our last problem, I would go ahead and switch these two values. Okay, so get your X on the other side. X minus 0.27, still cubed, equals 0.18 squared over 0.30. So I'm just flipping those two numbers, moving them. So we can now simplify the right side of our equation. 0.18 to the second power squared divided by 0.3, and that gives me 0.108 on the right side. And then on the left side we have X minus 0.27, and that quantity is still cubed. So from here, your easiest thing is to cube root both sides. Announcement.
Charles Fitzgerald, please report to the front of the school. Your parent is waiting. Charles Fitzgerald, please report to the front of the school. Your parent is waiting.
Well, that's fun. Okay, so we're cube rooting this. It gets rid of the cube there. So we have X minus 0.27, and we're going to cube root the other number, 108. So easiest way to cube root is to raise it to the 1/3 power, which is 0.48 or 476, because we got 3 sig figs. So 0.476, keep as many digits as we can for now. And then we need to add this 0.27 to the other side. So 0.476 plus 0.27, that would round us to 0.75 because we're adding, we need only 2 decimal places there. So that's our x value, all right? Now we want to check what our question was asking. In this case, what was the concentration, original concentration of O2? The original concentration is represented by x, so our concentration of O2 is equal to our x value, 0.75, and it is a concentration, so molar for its units. Oh my goodness, you guys couldn't see half of that. I'm so sorry. Okay, so let me backtrack a little bit since you couldn't see it. Just realized that. So we've got our x minus 0.27 cubed, and I simplified the right side, 0.108. Cube root both sides, so we can simplify the left, and we get 0.476. Add the 0.27 to the other side, so we get x equals 0.75. And so since x is our oxygen value, that is our concentration for oxygen. All right? So using x is kind of an interesting thing, and allows us to kind of backtrack and find other concentrations. So you can do number 2 and 3 here, again for practice, and then let me know if you have questions on that.